You've probably heard it 100 times. Astronauts come back from space slightly younger than the rest of us. They throw around that number 2.007 seconds like it's some kind of cosmic souvenir. It sounds cool, sure, but what if I told you that the story you've been hearing for a decade is completely backwards? What if the most famous number in space physics is actually a lie we've all been telling ourselves? The truth is the exact opposite, and it's about to change the way you look at the phone in your pocket. NASA ran one of the most ambitious medical experiments ever conceived, and it centered on two brothers who look exactly alike. Scott and Mark Kelly are identical twins, both former astronauts, both built from the same genetic blueprint. In 2015, NASA sent Scott to the International Space Station for 340 straight days while Mark stayed on Earth. For nearly a year, one brother orbited 400 kilometers above the planet while the other lived a completely normal life groundside. And when Scott finally returned in 2016, scientists compared their bodies down to the last cell. The headline result was stunning. Compared to Mark, Scott had aged about 13 milliseconds less. That's right, 0.013 seconds young. Not because of some gimmick, but because of the strange physics of time dilation that Einstein predicted over a century ago. But the study, published in the journal Science in 2019, revealed far more than just a brief victory over the clock. His telomeres, the protective caps at the ends of DNA, actually grew longer in space, then shortened again once he landed. A finding pulled together by researchers from 10 universities and research centers across the United States. The man came back biologically different on multiple levels, and yet nobody on that research team claimed the dramatic 0.007 second figure that keeps floating around the internet. So here's the question that should make you pause. If he genuinely came back younger, why does the number everyone quotes not match what NASA actually measured? The answer, as you're about to see, flips the entire story on its head. Picture two fighters pulling at opposite ends of a rope. On one side you have velocity and on the other gravity. That's the real battle happening above your head every second. The International Space Station is moving at about 7.66 kilometers per second, which is roughly 27,576 kilometers per hour. At that insane speed, time itself starts to slow down for the astronauts on board. According to calculations by NASA physicists, this velocity alone makes their clocks tick slower by about 0.7 seconds every 6 months compared to someone standing on the ground. So far, that matches the rumor you have heard. But wait, here is where the story flips. There is a second player in this game, and it works in the opposite direction. Gravity also bends time. The closer you are to a massive object, the slower time moves, and the farther you get, the faster it runs. The Sun, which is more than 333,000 times heavier than Earth, slows time down by 0.002 seconds every single year at its surface compared to our planet, according to NASA Goddard. Now, the ISS is orbiting at 400 kilometers up, far from Earth's gravitational grip, so the pull there is weaker, which means time should speed up. So we have one effect pushing time forward and another dragging it back. This is not a simple calculation, it is a tug-of-war. Most people never hear about the second force, so they assume the answer is obvious. But the truth is that the outcome of this cosmic match is not what you think. Let's see who actually wins this fight. You've probably heard the same story 100 times. Astronauts come back from space younger than everyone else. It's the coolest fact to drop at a party, right? And the number everyone loves to throw around is 0.07 seconds. That tiny, almost unbelievable sliver of time that supposedly shaved off your age. But what if I told you that this popular idea has been misleading you for years? Here's the real twist that will change how you look at everything, from science headlines to the phone in your pocket. The logic seems simple, but it's built on a trap. The 0.07 second calculation from NASA's physics notes is real, but it's only half the story, and it's the half that's missing the bigger picture. You see, that number only accounts for the speed of the International Space Station, which does slow time down by about 7 microseconds per day. The thing that everyone conveniently forgets? The ISS is also sitting at a 400-kilometer altitude, where gravity is weaker, and Einstein's general relativity tells us that weaker gravity means time runs faster. So now you have two forces fighting each other, speed pushing time backward and altitude pushing it forward. Which one wins this cosmic tug-of-war? Here's where the truth flips everything you thought you knew upside down. At that altitude, the gravitational effect makes time run faster by 45 microseconds per day, completely overpowering the 7 microsecond slowdown from velocity. The math nets out to a staggering 38 microseconds per day older, not younger. That's right, the net effect for an astronaut on the ISS is that they return roughly 0.007 seconds older after 6 months, not younger. The iconic claim floating around the internet is not just slightly wrong, it's backward. And the source is NASA Technical Reports from 2020, which breaks down this exact calculation to show the direction of time is opposite to what everyone believes. Now, you might want to see this for yourself, and here's the beautiful part. You don't need a rocket to feel the fabric of space-time bend. You can simulate this experiment in a 20-story building with a $500 civilian cesium atomic clock, the kind you can borrow from any technical university. Place that clock on the ground floor, let it run for exactly 24 hours and record the time. Then take it to the top floor, let it sit there for another day, and bring it down to compare against your reference. The result will show a tiny difference, roughly 1 nanosecond, for every 10 meters of height, proof that Einstein's prediction is happening beneath your feet, right inside your own apartment block. So the next time you hear someone bragging about how astronauts stay youthful, you can tell them the truth. The exact opposite is happening, and the entire story you believed is just a well-meaning rumor. Every single thing you thought you knew about the ISS and time has been flipped. And this misunderstanding does not stay stuck in orbit, it follows you down to street level, and it changes the way you use your phone every single time you ask it for directions. You tap open your Maps app, grab your phone, and ask it to take you somewhere you have never been before. Without a second thought, it tells you exactly where to turn, and you simply follow it, trusting the process completely. But the system that makes this possible is far more fragile and mind-bending than the smooth interface suggests, because every sat overhead is actually fighting a war against time itself. The atomic clocks on GPS satellites are not just keeping time, they are experiencing it differently, and the physics that corrects them is the only reason you are not endlessly lost. High above you, at an altitude of 20,200 kilometers, those satellites are moving at a staggering 3.9 kilometers per second. And according to MIT's School of Engineering, this incredible speed slows their clocks down by about 7 microseconds each day. Yet, because they are so far from Earth's gravitational pull, time actually speeds up for them by a much larger margin, gaining about 45 microseconds daily, which means the engineers have to bake in a net correction of 38 microseconds every single day to keep your location accurate. Now, imagine for a second what would happen if they just ignored Einstein. According to a 2017 report from Physics World, the error in your GPS would grow by roughly 10 kilometers every single day, which sounds bad enough until you realize the system would become completely useless in just 2 minutes flat. 2 minutes is the time it takes to boil a kettle, and in that brief window, the entire global positioning network would be rendering the wrong street, the wrong city, the wrong everything. That is the silent, invisible dependence we have on a theory that most people only half remember from a high school physics class. And this isn't a small-scale operation either, because the US government's official GPS.gov portal confirms that as of 2024, the entire global navigation constellation, including GPS, GLONASS, Galileo, and Baidu, consists of at least 75 active satellites, all of them running software coded back in the 1980s to correct for these relativistic effects. You have never seen a single one of these machines, yet your entire daily movement is shaped by their calculations, a quiet ballet of adjustments that you benefit from without ever knowing it. But you do not have to take their word for it, because you can actually try to catch this effect yourself, and it is easier than you think. Grab any smartphone with a professional time sync app like ClockSync that claims an error margin of around 5 milliseconds, and take a screenshot just before you board your flight. Now here is where the fun begins. Book a trip from Hanoi to London, flying west or head east from Hanoi to Tokyo, as long as you are in the air for at least 4 hours at a cruising altitude of 10 to 12 kilometers. Once you land, pull out your phone and compare its time to the local ground time at the airport, because the theoretical difference you are looking for is somewhere between 100 and 200 nanoseconds, a blink of an eye so brief that no commercial phone could truly measure it, which is exactly why you would need to repeat the exact same journey 10 times and average the results to see anything meaningful. Just remember that this is purely an illustration, because that level of time distortion is only detectable with specialized lab equipment. Yet the thought alone is enough to make your head spin. The next time you step outside and your phone tells you to turn left, just remember that you are trusting the work of a man from a century ago, and he is the one making sure you actually arrive at your destination this morning. In 1905, a 26-year-old patent clerk in Bern, Switzerland, quietly rewrote the rules of the universe, publishing a paper called On the Electrodynamics of Moving Bodies, which laid out his theory of special relativity, a mind-warping idea born not in a university lab but in a mundane office reviewing other people's inventions. 10 years later, in 1915, he went even further, unveiling his general theory of relativity, which proposed that gravity itself is just the bending of space and time, a concept that completely replaced the Newtonian framework that had ruled physics for 200 years. But how could anyone ever measure something so abstract? In 1949, Harold Lyons and his team at the National Bureau of Standards, now known as NIST, built the first atomic clock, a machine that took up an entire room and was so precise it could finally detect the incredibly tiny shifts in time that Einstein's equations predicted, a far cry from the cesium clocks small enough to fit in your palm today. Then came the space race, starting with the Soviet Union's launch of Sputnik 1 in 1957, and by the year 2000, the ISS had a permanent human presence, meaning for 24 straight years there have been living beings orbiting our planet, experiencing a time dilation that is observable only in that unique environment. Even Greenwich, the historic home of timekeeping, embraced the new physics, broadcasting time signals from atomic clocks beginning in 1955, and forcing astronomers to carefully account for relativity when comparing their readings with observatories across the globe. So, who would have guessed that a man pushing paperwork in a Swiss office would end up governing the entire clockwork of our modern world? You have probably heard that time is flexible, something bendable, but have you ever really stopped to question how we know? For decades, the theory was just math on a chalkboard, until someone decided to put it inside a flying machine. The first proof came not from a lab with lasers, but from 4 clunky clocks strapped into commercial airplanes, and the results were so weird that the world of physics had to rewire itself. What those clocks showed would turn Einstein's wildest scribbles into the most precisely measured fact in human history. In 1971, Joseph Hafele and Richard Keating took 4 atomic clocks and put them on ordinary passenger flights, one going east, one going west, circling the globe. When the planes landed, they compared those clocks to the ones that had never left the ground at the US Naval Observatory. The clock that flew east had lost 59 nanoseconds, while the one that flew west had gained 273 nanoseconds. And just like that, relativity was no longer a theory, it was a measured reality. But if you think you need a jumbo jet to see this effect, think again, because a basement in Harvard proved it just by going up a few floors. In 1959, the famous Pound-Rebko experiment showed something almost unbelievable. A clock in the basement of the Jefferson Building runs slightly slower than a clock on the 4th floor. They measured the shift in photon frequency over a tiny distance of 22.6 meters, and that single measurement confirmed that gravity itself, not speed, can bend time. And the madness doesn't stop there, because a team in Germany has built an elevator just to watch gravity steal time. The Einstein elevator in Hanover, completed in 2023, drops atomic clocks from a 60-meter tower, proving that time changes even over a distance of just a few dozen meters. Yet the most mind-bending demonstration came in 2019, when Stanford researchers placed clocks at the top and bottom of a chair that was only 1 meter high, and the top of that chair aged 100 attoseconds faster every single day. Now here is the part that breaks the brain. Even gravity's pull inside a spaceship is playing tricks on spacewalkers. When 2 astronauts float outside the ISS at 400 kilometers up, they are moving at 7.66 kilometers per second, but they also experience gravity that is 10% weaker, and that combination makes their time run faster than the crew inside the station. NASA has documented this strange paradox in actual technical reports, meaning the universe is not just a playground for scientists, it is a machine that can be measured from a laboratory floor to a chair in a clean room. So what does all of this prove? It proves that science does not ask you to believe, it only asks you to measure. But if time can change over a single meter, why are we still so sure that it stays the same for all of us? You have probably heard the phrase twin paradox thrown around in science discussions, but do you actually know where it comes from? Or is it just another concept people nod along to without understanding? The term was first introduced by physicist Paul Langevin back in 1911, only 6 years after Einstein published his theory of special relativity, according to the American Physical Society. It sparked endless debates until real-world experiments finally backed it up in 1971, but the confusion around it never really disappeared. Have you ever wondered if the things you believe about space travel are actually true, or are you just repeating what you heard somewhere? Let's clear up one of the most common mix-ups, the idea that astronauts get taller because of time dilation, which is completely false. Russian cosmonauts on the Mir station and the ISS were measured an average of 3 to 5 centimeters while in space, as documented by NASA in 2021, but this happens because their spines expand without gravity compressing them, not because time is moving differently. To make it even clearer, when Scott Kelly returned from the ISS in 2016, he stood 5 centimeters taller than his twin brother Mark, according to NASA follow-up measurements. Yet that height vanished within 48 hours of being back on Earth. The permanent effect of time dilation is microscopic and has nothing to do with your bones, so these two very different phenomena get tangled up in people's minds far too easily. Another widespread misunderstanding is that astronauts can somehow sense time slowing down, but that idea falls apart the moment you look at the numbers. The effect on the ISS is only 7 microseconds per day, which is 0.000007 seconds, and detecting that requires a cesium atomic clock accurate to 1 second in 100 million years, as the National Institute of Standards and Technology confirms in 2023. No human body, no matter how trained, could ever perceive a difference that small, so anyone claiming they feel time stretch while orbiting is just imagining things. If you think about it, do you really believe your brain could register something 1,000,000 times smaller than the blink of an eye? There is also a fascinating historical misunderstanding about the ether, a hypothetical medium that scientists in the 19th century were absolutely convinced carried light through space. The Michelson-Morley experiment in 1887 is now celebrated as one of the greatest successful failures in science, because it proved the ether did not exist and accidentally paved the way for Einstein's revolution. As noted by the Smithsonian Institution, it took years of stubborn belief before the scientific community accepted they were wrong, and the same pattern of denial continues today with so many popular misconceptions about relativity. Even geniuses need time to be proven right, and sometimes the most brilliant minds are the ones holding on to the oldest illusions. Imagine more than 4,000 kilograms of space junk hurtling around Earth at 28,000 kilometers per hour, each fragment carrying its own tiny warp in time. That is the reality we live in, and the European Space Agency's Space Debris Office logged every bit of it by 2023. A single stray bolt traveling at that speed could slam into the International Space Station and cause $100 million in damage, which is why tracking these objects means tracking their relativistic drift too. It sounds absurd, but this debris field is a direct consequence of the same physics we have been chasing. Now here is a moment where the theory stopped being academic and became a trillion-dollar headache. In 2018, the European Space Agency launched 2 Galileo satellites, numbers 14 and 15, into the wrong orbits. The mistake forced engineers to recalculate the relativistic clock corrections on the entire constellation, and that single error burned through an extra 10 million euros just to keep the system honest. You realize then that every satellite company on Earth is completely dependent on Einstein, not as a philosophical footnote, but as a line of code in their navigation software. But what happens when we push the measurement even further? The Max Planck Institute for Extraterrestrial Physics in Germany proved back in 2010 that time dilation from velocity can be measured down to 10 to the power of -16 seconds, using optical clocks riding on satellites. That kind of precision opens the door to future navigation systems accurate to within a single centimeter, which sounds incredible until you hear what comes next. In 2024, researchers at Princeton University trapped strontium ions and discovered they could detect time differences even when the ions moved at just a few centimeters per second. That breakthrough points directly to seismic sensors and mineral exploration, meaning the same effect that ages astronauts is now being used to map what lies beneath our feet. And yet the clearest picture of this strangeness comes from comparing 2 very different altitudes, a GPS satellite at 20,200 kilometers and the ISS at just 400 kilometers. Astronauts on the station feel the speed more than gravity, netting out to a time that runs faster overall, while those GPS birds need a correction of 38 microseconds per day in the opposite direction. We live in an era where a difference of a few hundred kilometers flips the direction of time itself. The future of life on Earth now depends on these impossibly small numbers, and somewhere up there, every piece of junk is ticking to a different beat than the one on your wrist. The first atomic clock was built in 1949, a machine so large it filled an entire room, a far cry from the cesium devices we can hold in the palm of a hand today. It was this leap in precision that finally gave scientists the tools to prove Einstein's wildest ideas, transforming abstract theory into measurable reality. But how far have we truly pushed our ability to slice time into ever finer pieces? In 2001, a team led by Ferenc Krausz at the University of Vienna defined and measured the attosecond, a unit of time so fleeting that it represents a billionth of a second, opening the door to observing the movement of electrons themselves. With this incredible resolution, we can now detect the time dilation between the top and bottom of a simple chair, a distance of just 1 meter, proving that gravity's effect on time is happening all around us, constantly. This precision is built on the ultimate cosmic speed limit, the speed of light, measured at exactly 209,792,458 meters per second, a constant that Einstein declared nothing with mass could ever surpass. The very definition of the meter, our fundamental unit of distance, is now derived from this fixed speed, tying our entire system of measurement to the immutable laws of physics. Our mastery of time has also forced us to reconcile our atomic clocks with the slow, chaotic spin of our own International Atomic Timescale, having to add 27 leap seconds between 1972 and 2016. It's a fascinating admission that time is not a fixed global constant but a negotiable number, even here on Earth, where we must manually adjust our perfect atomic clocks to match the imperfect reality of our solar system. The accumulated effect of a life in space becomes more tangible when we look at the record of Gennady Padalka, the Russian cosmonaut who spent 878 days in orbit across 5 missions. That incredible time in microgravity, traveling at immense speeds, means he is roughly 0.024 seconds younger than he would have been had he stayed on the ground his entire life. Each of these advancements, from a room-sized machine to an attosecond, brings us closer to understanding that we are living in a world measured down to the billionth of a second. A world where the very fabric of time is relative to our place in the universe. You step up to the window of the International Space Station and there it is, Earth, glowing blue and white against the absolute black of space, and you watch the sun rise and fall 16 times in a single day. That is not an exaggeration. The station completes an orbit every 92.9 minutes, per NASA's Earth observation data from 2024, so the horizon you see from that cupola is a relentless, breathtaking loop of light and dark. Think about what that does to a human body that evolved to run on a 24-hour cycle, because your circadian rhythm is now screaming that something is deeply, profoundly wrong. So the crew does not try to sync with the sun. They cling to a reference point that makes sense, which is UTC, Greenwich time, and they set their phone alarms to wake them up at a specific hour, even though the sun is rising outside their window for the 8th time that day. You try to sleep for 8.5 hours every night according to that clock, a number NASA has recommended since their sleep studies began in 2001. And you do it in a tiny soundproof booth strapped to the wall, because the alternative is drifting into your crewmate's equipment. It is a fascinating separation. Your biology insists on a rhythm that has nothing to do with the physics of the universe you are actually in. Now, what about the time dilation we have been talking about? In 2023, NASA's profile of astronaut Frank Rubio noted that his record-breaking 371 days into space made him younger by about 0.014 seconds, compared to if he had stayed on the ground, a number so small it feels absurd. And if you look at Sunita Williams, who set the female record with 322 days in 2012, her theoretical age shift is a similarly minuscule amount, far too tiny for her body to ever register. They cannot feel time bending, but they can see something more profound. The sun rising 16 times a day, a visual impossibility that makes the abstract theory of relativity feel like a physical, tangible truth. The clock on the wall is a lie, the sun in the sky is a liar, and the only thing they can trust is a vibrating alarm on a phone. They don't feel time, but they see it through that window, 16 times a day. Have you ever wondered what it would actually feel like to travel through time, not in a wormhole, but strapped into a seat on a commercial flight? We've all seen the movies, but the line between science fiction and our reality is blurrier than you think. And it's all written in the language of Einstein's relativity. In 2014, Christopher Nolan's Interstellar brought the concept to the big screen, with Nobel Prize-winning physicist Kip Thorne as the science advisor, and they showed us a planet where 1 hour equals 7 years back on Earth. It's a staggering thought, but that cinematic fiction is rooted in a physics so precise that it governs everything from the GPS in your car to the cost of sending a human into orbit. So let's step back from the blockbusters for a moment and consider a hypothetical spaceship that could push the limits of physics itself, asking what would really happen to the people we leave behind on the launch pad. Imagine an astronaut who boards a ship and accelerates to 99.9999% of the speed of light, spending just 1 year on board according to his own clock. When he returns to Earth, he would find that 707 years have passed, meaning a younger brother born after his departure would be centuries older than him by the time of the reunion. This is not a plot point from a novel, but a direct calculation from the Lorentz factor, a standard result taught in physics lecture notes at institutions like the University of California, Riverside. Now, let's bring that mind-bending scale down to something you might actually experience. A Boeing 747 cruising at 900 kilometers per hour from London to New York. A flight that has been measured to shift a passenger's clock by a few nanoseconds compared to someone who stayed on the ground. This isn't just theoretical. The effect has been practically verified in commercial flights back in 1971 and again in 1996, making it the most accessible proof that our movement through space directly alters our passage through time. But if these changes are so tiny, why do we pour billions into understanding them? And what does it cost to even send one person into this shifting river of time? The reality is that keeping a single astronaut alive on the International Space Station costs roughly $7,500 per hour just for life support. And NASA's annual budget for the entire ISS program is about $3.1 billion, all spent to study effects that we cannot feel but absolutely cannot ignore. So, if we can barely measure the time dilation on a commercial jet, and it costs a fortune to study it in orbit, what is the real price of turning these sci-fi dreams into our daily reality? The cost of chasing these cosmic effects isn't just in dollars or nanoseconds. It's in the gap between what our senses tell us and what the universe actually does, a gap that grows wider the faster we move. Science fiction is slowly turning into science fact, but the price we pay to bridge that gap is measured in billions of dollars and impossible centuries, leaving us to wonder if we're ready for a future where time itself is a currency. We started with a rumor about astronauts coming back younger, a tiny number whispered across the internet. We dug into the real story of Scott Kelly, the NASA twin who actually aged less but by a margin so small it defies intuition. Then we uncovered the cosmic tug-of-war between speed and gravity, a battle that determines whether time moves faster or slower for anyone orbiting Earth. And the truth turned out to be the opposite of the myth. Those astronauts aren't returning younger at all, but ever so slightly older, a fact that rewires how we see the heavens. Time, you see, is not a steady river flowing for everyone at the same rate. It is a variable, bending and stretching depending on where you stand and how fast you move. This is not a philosophical idea, but a physical reality we rely on every single day. The GPS in your phone, the system that guides you to a coffee shop or a friend's house, would fail within minutes without accounting for this strange flexibility of time. Einstein's wildest thought experiment is now the quiet engine behind your daily commute. So, the next time you glance at your phone to check the time or your location, remember, you are holding a device that only works because we understood a truth that flipped our common sense on its head. You were told you were tricked, and you were, but not in the way you expected. The trick was that the story was backwards and the reality is far more fascinating. Now, let me ask you something. Imagine you could board a ship and travel at nearly the speed of light for just 1 year. By the time you returned, 7 centuries would have passed on Earth. Your younger brother, who was just a child when you left, would be long gone, while you would have barely aged. How would you feel stepping back into a world that no longer knows you? Think about it and share your answer in the comments below. The journey we took today from a pair of twins to satellites in the sky ends with a simple realization. Einstein was right, and after this, you will never look at a clock the same way again.